here I want to talk about really the roles of hydrogen in this global decarbonization effort. And I want to talk about why we're excited about hydrogen and what are the challenges and the current status. I'll give you an overview about what people are envisioning hydrogen can help with this global decarbonization in different sectors of our industry. And then I'll talk about the three parts about hydrogen, kind of like the supply chain of hydrogen from production to storage and transportation, and finally to the utilization. And each of them have their own challenges. And finally, I'll give a summary about the perspective. If we can make hydrogen cheaply without a lot of carbon, what could be the future? So for the whole energy is really due to this dual challenge, right? We want to have an even more prosperous life. That means we need a lot of energy at the same time as we need a lot of energy that also causing consequence on the environment. And currently it's really a good time. I would say for the next decades is a golden time for energy. Not only because of our administration put a lot of emphasis on energy, like Biden administration have launched a number of Earth shots focused on different parts of energy. Hydrogen is the first Earth shot. And also the companies have committed climate goals. They all have their goals for achieve net zero by different decades. And at Stanford, we have this new Doerr School of Sustainability that focus on climate and sustainability. So no matter from the countrywide to the worldwide to the local eco-environment, energy is a big topic. I want to focus on hydrogen. This is kind of the fabric of Stanford energy research. If you look at the vertical columns, those are different areas that focus on energy. For example, there are bits and watts related to the grid. And there is a storage X focused on battery, other means of storage, natural gas, etc. And then the hydrogen is regarded as a potential green fuel for the future. For all of those energy technologies, there are different disciplines involved, not only have finance, politics, education, data, etc. So this is really an integrated problem, and there are integrated solutions that we have to think about for hydrogen. So since we're talking about hydrogen, let's think about what is hydrogen. Hydrogen actually is the most abundant element in the universe. No matter from the mass perspective or from the molar perspective, right? They're 70 and 90% of the universe. And actually, we all get our energy indirectly from hydrogen. If you think about our energy is from the sun, in the sun is really the fusion, right? It's the combination of the hydrogen atom to helium, right? I mentioned about the mugs, right? The first one is hydrogen, the second one is helium. What's the third one? Lithium, right? That's the battery one, right? So it's the two hydrogen come together, form the helium, and that's a very exothermic process, and that gives us the primary energy in the sun, and that gives the energy to the earth, right? Hydrogen is not stable, so on Earth, the atmospheric and the Earth environment are not reactive. So hydrogen does not exist in the elementary form. Rather, they exist in the stable form. What are the stable forms for hydrogen? H2O, water, right? Water has hydrogen. What else have hydrogen inside? Oil gas, right? All the oil gas, right? All the oil gas are called hydrocarbons. Means they contain hydrogen and the carbon, right? So oil and gas, why they're so predominant in the energy landscape, because they are very convenient. They carry this hydrogen mostly in the liquid form. It's very easy to transport and use. Okay? But we don't see natural hydrogen that much. We do have a little bit natural hydrogen. Have anyone heard about geological hydrogen? Probably not. In places they have a lot of geothermal, for example, Yellowstone. You know we have natural gas, right, is bubbling through the Earth. But in places they have a lot of geothermal, they find some of the gases actually contains hydrogen, sometimes contains high concentration of hydrogen. So people are thinking it's probably due to the rock. Some of the rock contains iron, and they react with water, and that reaction actually forms hydrogen. So there is increasing interest to understand this geological hydrogen, right? If we can dig and get hydrogen, that will be fantastic. Hydrogen is considered a green fuel because there is no carbon, right? When you oxidize it to water is the way to release the energy in hydrogen. It only produces water. When you burn hydrogen, actually hydrogen flame itself is not visible. It doesn't give any colors. What gives the color of a flame? Impurities, right? Something has there to give the colors. If you see some yellow and the reddish color is many flames, they will produce soot like a carbon. You see the smoke. And that radiation of that one gives those colors. That's one of them, right? So when you see a candle flame, you see a lot of yellow things. But if you burn a propane torch, you see a lot of green flame, especially if you have a gas range, you have a green flame, you don't see yellow ones, right? That's because of some of the radicals containing carbon, the chemiluminescence. When you have those radicals, they give out color. So for hydrogen, they don't have these carbon-containing things. So itself doesn't have color. And it's very flammable compared to other hydrocarbon fuels. It burns very fast, right? So all those things make it different with natural gas. If we have a natural gas burner at home, we cannot just switch to hydrogen. It burns fast, it will flash back. It can be dangerous, okay? So switching to hydrogen is not that straightforward. If we think about hydrogen, because hydrogen is very light, when we count the energy density, depends on how you count the energy density, right? You can define based on mass-based, per unit mass. In that case, hydrogen energy density is very, very high. It's 3 times higher than the gasoline or diesels. But if you count energy density in terms of volume, what do you think? It's very, very low because it's just because of the same factor, right? Hydrogen has very small density. Why do we care about energy density in terms of mass and the volume? Storage, right? The size, right? Whenever you think about something has very small volumetric density, to have the same amount of energy, it needs a huge size, right? So it makes it very difficult to store, to transport, etc., right? If you're going to hold the hydrogen in the airplane, you don't want the airplane to have a huge storage of hydrogen. And that not only increase the volume, but also increase the mass, right? All the things to contain that things make it very difficult. Hydrogen versus air is very light. So if there is a leakage, the nice thing is hydrogen will tend to escape, right? Compared to others. So those things are those properties are the opportunities, also the challenges for us to think about hydrogen. We'll see that in the later part. So if we think about greenhouse emission, this is kind of relatively complicated. What we have here is the top 2 are the global greenhouse emission. The very left is based on the gas. So you can see the biggest pie, the blue one, is carbon dioxide. Okay? And in addition to that, we also have methane and nitrous oxide. And the bottom are the US. We can just look at the global one as an example, right? If we look at the by sectors generation, we can see there is electricity, there is agriculture, there is transportation, industry, etc. So when we think about hydrogen, is really think about how hydrogen can impact all those sectors. If hydrogen have the potential to reduce CO2 emission from all those sectors, right? If we think about electricity, right? How do you think hydrogen can help with the electricity part? Yeah, hydrogen itself can generate electricity. Instead of burning it, you can run hydrogen through a fuel cell to generate electricity, right? And that can be used for backup powers, right? Instead of using diesel generators that populates the campus. So pay attention when we have a power outage, just hear the loud noises. Those are diesel generators, right? We could potentially think about hydrogen as a way to generate backup electricity. The second one is saying if we have excess electricity from either renewable or even nuclear, we can use hydrogen as a storage media, right? We can use electrolysis, using the electricity to generate hydrogen to store the energy for long term, right? So that's how we can help with electricity. What do you think about transportation? So you just talk about the potential there, right, for heavy-duty, long-range transportations, right? But the challenge is how can you store it on board so you can carry them enough, right? So for passenger cars, I think there is a consensus that the battery car is going to dominate. But for long range, for cargos, right, if you think about the trucks on the road, their main purpose is transport goods, right? They need to carry the whole thing with mass. We don't want to use that to carry batteries, right? Even though battery has high efficiency, you have to think about how much of that energy efficiency is used to carry a battery versus useful things. For passenger car, it doesn't matter. Your weight compared to the car weight is nothing, right? But for cargos, it's very different story. Right? So hydrogen has a potential there. And also there is another, it's not exactly for transportation, but it's for forklift, for things is stationary. You don't want a lot of charging downtime, and the hydrogen can be one for those things. Like Caterpillar is actively looking at hydrogen fuel cells to power their equipments. And also their industry, right? Hydrogen can provide heat, can use as a fuel for many of the process. Okay? For residential, is really kind of, you mentioned, is blending hydrogen with nitrogen for heating, potentially cooking, etc. Because of those potentials, that's why we're interested in hydrogen, right? For example, when we think about hydrogen as a storage media, when we compare it to batteries, so here we're really looking at the duration versus the capacity. The battery is great, right, for shorter days. But as we all charge our phones, right, if you just leave it there fully charged for a week, the battery will drain, right? That's the inherent problem with battery. If we want to store this for a long time, we have to go to some chemical ones or maybe some compressed air over there. So hydrogen really have the ability to store energy in large quantity over a long time, and that gives the potential to transport energy from one place to another place. For example, in Australia, they have a lot of wind, they have a lot of solar, and their weather is very similar to the Bay Area, right? They have a lot of excess renewable energies. So when their renewable energy is very, very cheap and their battery is used up, they're really thinking about using that cheap renewable electricity to generate hydrogen. The cost there is now the concern in that case, and they want to transport those hydrogen to Japan where they don't have a lot of resources. Right? That's kind of one business model for hydrogen. This is a vision provided by Toyota. It's kind of looking at the supply chain of hydrogen as the things we mentioned. From the production, there are dominantly two ways. At the very top is still using fossil fuel to produce hydrogen, but keep that carbon captured and sequestrated, potentially utilized. The middle part there is really using all kinds of renewable energy and does electrolysis to produce carbon-free hydrogen, right? So now both of them will be carbon-free hydrogen. The top one is the blue hydrogen, the middle one is green hydrogen, right? And then once we have those hydrogens, then is storage and transportation. You can see there are several things listed there because we don't have a consensus about what's the best way to transport hydrogen. The top option is saying using liquefied hydrogen or compressed hydrogen, using this physical form to keep it very, very high pressure or even low temperature to increase the amount of hydrogen we can transform. The bottom three is using chemicals, react hydrogen with something else such that it's a liquid, for example, ammonia. Then it's very easy to transport. Once we have those things, the potential utilization is the top two is like electricity, like fuel cells, and the trucks, etc. And you can also use it for heat. So at Stanford, we have a hydrogen initiative which really want to look at the challenges and the opportunities with hydrogen supply chain and then try to doing research, try to facilitate the hydrogen here. And we have people work on production, storage, application, and the policy, etc. I'll move on to talk about hydrogen production. The first thing is, what are the goals for hydrogen production, right? The goal is, as I mentioned, is by the Department of Energy. They set this Earthshot. They set a goal called the 111. Okay? It's very easy to remember. 111 means we want to have $1 per 1 kilogram of hydrogen in 1 decade. Right? So that was already 2021. So by 31, that's the cost. In that case, we consider hydrogen to be cheap enough, to be economic enough. But the key thing here is not just any hydrogen. They want clean hydrogen. They want carbon-free hydrogen to be in that cost. Currently, if we don't consider carbon-free, we are already around that range. Okay? We're already about $1. So this is kind of, we look at how much hydrogen we need to produce, right? You look at the trend of the global hydrogen production, roughly is a linear function, right? We have increasing demand, and we think that will continue to increase as more industries want to use hydrogen. So if we look at each year, there are 2 bars, okay? The higher bar means they're using pure hydrogen. Okay? For example, for ammonia synthesis, right? Ammonia is the biggest thing for fertilizer. So you can see almost more than half of hydrogen is used for ammonia. So ammonia and hydrogen are closely coupled together. So that's why people are thinking about ammonia can be a carrier for hydrogen. And the red part is refining. It's used to refine the crude oil to generate gasoline and the diesel, etc. Okay? The shorter bar there means they are using hydrogen in the mixtures. Okay? They don't need a very high purity hydrogen. And there you can see making methanol, and then there is another bar is kind of purplish here. It's called a DRI. It's used for iron steel making. It's called a direct iron reduction. Okay? So that's how the industry decarbonization can come in, is using hydrogen for steel. So if you look at the current hydrogen production, we know how to make hydrogens, right? And here is we can make hydrogen from all the oil and the gas. We can make from coal, oil, natural gas, okay? And if you count, roughly about 95% of hydrogen is produced from those sources, okay? Only 5% is from electrolysis. Even in that 5% electrolysis, electricity, that is produced predominantly by fossil fuels. Okay, so if you count it, less than 1% of hydrogen actually is carbon-free. Okay, and just produce hydrogen itself, it produces about 2% of CO2 emission. When we make hydrogen, we have to consider many factors, the cost and the scalability, and CO2 emission, stability, lifetime of the systems, consumption of energy, and also water, right? We use a lot of water. And we also need to consider about purity and the pressure of hydrogen that impact the downstream process. So the dominant method is called the steam methane reforming. Is a very high temperature, high pressure process. It's a very scalable process. It takes natural gas, methane, and the water. In that case, they're using steam, very high temperature. So the first case is the very top reaction. They generate CO, carbon monoxide, and hydrogen, and that's the syngas. And then they further react with water, and in the end, they form CO2 and the hydrogen. They scrub away the CO2, and then they have the hydrogen. For this method, the cost is mainly affected by the natural gas cost. Because of the recent world events, natural gas cost has gone up quite a bit. But on average, this is about around $1 to $1.5. Okay, very, very close to the DOE target, but this is not carbon-free. This steam methane reforming, if combined with carbon capture, is going to be a rapid way to produce carbon-free hydrogen. The other one is called electrolysis. Electrolysis is blocked there is splitting water to hydrogen and oxygen. Okay? Again, this is endothermic reaction, means it takes energy to make this happen. Right? If we do it electrochemically, if you measure that energy in terms of volt, it takes about 1.23 volt thermodynamically. And there are many different types of electrolyzers. The first one is shown here. It's called alkaline electrolyzers. In this case, the whole thing runs in an alkaline solution, for example, potassium hydroxide. And it has a big diaphragm to separate hydrogen and oxygen to prevent them from mixing and potentially very reactive scenarios. And in this case, they have two electrodes, and they use mainly nickel. So this is cheap and this is scalable. It has over 100 years of history. The downside here is that diaphragm is very thick. So it has a lot of resistance. It cannot run on very high current density. It doesn't produce hydrogen very fast. So it doesn't couple with renewable energy very well. On the right-hand side is called proton exchange membrane electrolyzers. And that's where a lot of the focus and the startup companies are focusing on, or even a very mature company. So the difference here, instead of have that diaphragm there, here is replaced with a membrane. That membrane is tens of microns thin, right? So this whole transport resistance is significantly reduced. This thing runs on water, but the membrane is kind of acidic. So the whole environment is acidic. So this time electrolyzer is literally covered with all the noble metals, with gold, with platinum, with iridium, right? The things there is more expensive than your jewelry box because of only those things are stable in that very acidic environment. So their challenge is really, do we have enough supply of those materials? Can we lower the loading of those noble metals to make it affordable in this case? But because of the membrane is very thin, it can go very high current density. There is a startup called Electrical Hydrogen. They were like founders from Tesla or something, and they claim they can reach 10 ampere per centimeter squares. That's very, very significant. Again, that is related to the energy density, right? Their size can be much smaller. So if we compare the cost, left-hand side, and the CO2 emission, right? When we have the steam methane reforming with 90% of carbon capture rate, it's cheap, it's pretty good. Right? The coal is worse, right? If we have electrolysis, now it's very expensive. It's mainly related to the electricity cost. Currently, depending on where is the electricity, it's about $5 to $6 per kilograms. Okay? So it still has a long way to go there. There are many other companies trying to convert methane without releasing CO2. So the idea is if we keep the carbon in the solid form, then we don't have to capture this gas phase. Okay, so they're doing methane pyrolysis. At the very top, you see CH4, which is the natural gas major component. And then they split it to solid carbon and hydrogen, right? In that case, the solid and the gas can be easily separated, right? If that carbon, if it's of higher quality, if you make a carbon nanotube or graphene, then this whole thing can become more profitable, okay? So this is a company called Monolith, is students from Stanford. They founded, and they are working on this technology. So Stanford has a range of faculties working on different ways of producing hydrogen. So that's about the production, right? We see the steam methane reforming is going to be important, but we need this carbon capture. I visited ExxonMobil in September, and they plan to build a blue hydrogen plant. What they're trying to do is to do steam methane reforming with carbon capture. They claim their carbon capture rate is about 95%. And their way of transporting that hydrogen is either use it in-house, or they are thinking about use ammonia to transport that hydrogen. Okay, so there are many companies are actually building this one. Let's look at the hydrogen storage and transportation, right? The challenge is really hydrogen is very, very light. I put the cotton candy there. When we think about the hydrogen, because it's very low density, when you convert sugar to cotton candy, you're not changing the mass, but what's changing? Volume, right? And to carry that cotton candy is much, much more difficult than carrying that little bit of sugar. And hydrogen is exactly the same challenge. When we look at all the energy carrier, we need to look at energy density. This is volumetric density. Gravimetric density means per mass, right? You can see hydrogen all settle near the lower right corner. They have very high gravimetric energy density, but very low volumetric density, okay? Just like the cotton candy. And if you look at the hydrogen, there's three things listed there. Liquid, 700 bar, 350 bar, right? You don't see a big difference between liquid and the compressed gas. Hydrogen has very, very low melting temperature. If we want to convert it to liquid, that's minus 259 degrees Celsius. It's almost close to 0 Kelvin, right? It's very, very close. If we want to cool down hydrogen to that low temperature, what do we do? Does it take energy? It takes a lot of energy, right? If we want to say, forget about liquid, we want to do gas, we want to compress it to 700 bar, does it take high energy? Right? Because of the fluffiness, when we compress it to high pressure, it takes a lot of energy, right? No matter what we do to store and transport it, it takes additional energy to do that. That's why it's so difficult. So there are generally two ways of thinking about hydrogen storage as a way either for transportation. There are the physical forms I mentioned, right? You can go very high pressure, compress the gas. You can go liquid, or you can go somewhere in between, either both high pressure and the low temperature, cryogenic. Okay? And then the other way is material-based, is let's absorb that hydrogen, bond that hydrogen into some materials. You see many fancy materials there, but none of them have reached the DOE limit because of hydrogen is very light. So currently, people are really thinking about methanol, ammonia, and another liquid organic carrier, mainly by Japan, as a way of carrying hydrogen by other materials. And ammonia seems to be the popular option because of the infrastructure of ammonia already well established. So if you see the Toyota car, Mirai, right? If you see where is the hydrogen, the green tank in the very back, okay? They are pressurized tank. There are 700 bars in there. And if you think about the trucks, we're thinking about the same. They're going to just stack all those tanks in here, right? We're going to have this high pressure gas in there. And the fueling station, of hydrogen fueling station, work with this very well. So it takes about 6 minutes to fuel it, right? Compared to battery. A battery can be hours. And then the nice thing about hydrogen is even though it occupies a lot of space, it doesn't carry a lot of weight. Liquid hydrogen, we have a lot of knowledge actually about liquid hydrogen because of the NASA. For the rockets, we have looked at the liquid hydrogen, liquid oxygen as the energy for rockets. So we know there is a lot of ways to transport and store liquid hydrogen. And as I mentioned, is if you think about hydrogen as energy carriers, there is really from the Australia that using their wind and the solar, and they want to transport that hydrogen to other parts of the world. So this is kind of what they're envisioning. One is if you want to transport liquid hydrogen, you can have this boat thermally insulated, right? Kind of like your water bottle. Much fancier version, much bigger version. Keep the liquid hydrogen there, right? And that's what's the real one is just like the pilot scale, right? To showing that. There is another way of transporting hydrogen people are thinking about is we have natural gas pipelines everywhere, right? If we can blend in hydrogen within the natural gas, then problem solved. And this has been done before in England, right? They have the town gas, they're already blending hydrogen into the natural gas. So this is one thing people are thinking about. The challenge here is, it's called the hydrogen embrittlement. Hydrogen is very, very light. It can actually get into the steels, the pipelines, and change the mechanical properties of the pipelines, make them brittle, right? So hydrogen is really, because it's so nimble, it can change a lot of things, right? So it's really a concern about how much hydrogen can we blend in there without changing the materials there. And for storage, if we want to store a large amount of hydrogen for a long time, people are really looking at salt caverns. Okay? Salt caverns is very low porosity, and there are a lot of salt caverns, especially in Texas, and that can keep hydrogen. Right? We talk about store CO2 underground, and also hydrogen stored underground, but they are very different animals. Okay? CO2 mostly inert. Hydrogen can be reactive. Hydrogen is very, very diffusive. Okay, CO2 may stay there, but hydrogen is much more, have a higher tendency to escape, right? So their storage underground have different challenges. Finally, I want to talk about utilization, right? There are cars, right? Mirai is not a popular, there are not a lot of sales, but there are a lot of potential for heavy duties, right? Trucks, like in the LA port, Toyota is working with them, trying to use the hydrogen-based fuel cell trucks there, buses. And what's surprising is what's most successful story about fuel cell vehicle is the forklift in the warehouse, right? Because we all want our package immediately, right? The forklift has to work nonstop. If you use battery, the charging is too slow. And they don't want to have indoor pollution. So hydrogen fuel cell is having a very good popularity with those indoor forklifts. As I mentioned, hydrogen can generate electricity. So for example, Microsoft is looking at hydrogen fuel cell as a backup power supply for their data center. And their companies are looking at the fuel cell planes and the boat, etc. As I mentioned in the very earlier, when we look at hydrogen production, I said there's one is called the direct ion reduction, right? Ion steel making itself produce about, I think it's 8% of global CO2 reforming. So instead of using coke to reduce the iron ore, there are a lot of interest of can we use hydrogen for the same purpose to remove that. So to summarize, I think it's truly exciting to look at the potential of hydrogens, and all those challenges actually present opportunities for us to explore, right, and innovate. That's what Stanford is good for. And if we can make hydrogen or increase the use of hydrogen, according to this Fuel Cell and Hydrogen Energy Association, we believe we not only will make the economic better, we are also going to produce a lot of job opportunities. And I think that's all I want to say about hydrogen part. Yeah.